Okay, so thanks everyone to be here. Before we start, slides will be online if you want to take notes, okay? But I will explain what I've done, like a story. So it's much better if you follow the story and you see at the end some interesting stuff that I found. So this is a 3 years long research on SSL, not on the SSL TLS, more specifically on RSA keys. It's not about crypto, it's about implementation of crypto and how crypto is perceived at the moment. And I used live data collected from several sources over a few years. So the idea is to go through a series of stuff that is simple example, big research, some data and some graphs, and then some conclusion, and then we can have some chat at the end. Okay, so why to check SSL TLS certificate? Because everyone says we want more encryption, we want to protect everything. So the amount of encrypted data is increasing, but we have no idea actually if the encrypted data is really secure. And we have no idea what it means encrypted data, usually, because we don't know how it's implemented or how it's tested. So, some basics. What is a cryptographic key? Nothing incredible. It's just numbers. And these numbers are usually based on prime numbers, so special numbers that that are divisible only by themselves or 1. Now, why is it important to check this? Because almost everything we're using now is using prime numbers, so some form of crypto. And there are no tests. There is almost nothing to check this kind of stuff, like cryptographic, correct implementation, or encrypted data, or how the system or the application are using it. Here are some of the many sources that people can use to collect keys. I used only, we can say, 5 of them instead of all the battery of systems, and I mentioned only the most common protocols. As a service, if you think about services, you can use like chat, mobile phones application, signed files, streaming application, keys for file encryption, key for system stuff like BIOS, UEFI. All of this is using cryptographic key, and we are going to talk about RSA keys. Now, first, some assumption. The assumption are if we do it, then somebody that talks about crypto should be an expert, or maybe is an expert. And maybe the people that are implementing it, maybe they know what they're doing, and maybe the application are using stuff that have been prepared by people that know what they're doing or by a good developer. All of this is 99% not true, and we're going to check this stuff because to check if crypto information and crypto implementation is correct, we don't need anything else other than data. We don't need even to know if the implementation is correct. We can see at the end if the result is correct or not. So we can start by saying, to test this, we have to collect information, decode what we have, parse it somehow, so human can read it and check it, and then see if there is something that is not okay. Now, I'm based in Europe, so there are some strict rules. First, we check only numbers, and cryptographic numbers are very big numbers. Normal application cannot handle this kind of number. Normal programming language cannot handle this kind of number. You have to do some special stuff to make it useful, to make the application or the system able to handle them. Then, because we're in Europe, there will be no correlation. So it means I will not point finger, and I will not connect stuff on what generated this and what this can be used for something. For example, I found a broken application that has a broken key, and that broken key can be correlated with a company, with an application, or with something. We will not look into that, only numbers, and no attribution. I will not say anything about what is broken or who did something wrong. Okay, so the idea is collect a lot of data. To collect this, I used some services that are available online. One is cans.io. They have tons of information. I get their keys because they collected it for free, and they make it available to everyone. Then I installed IDS. In this case, I use Suricata to intercept traffic generated by applications. And I instructed IDS to dump everything that has a SSL TLS encryption key. And then I downloaded a copy of all the PGP and GPG keys available to the public and used for encryption. So where PGP keys are much smaller than the amount of keys that are available for services for browsers, so we start with a PGP key. The data set of PGP keys is around 4.5 million keys, but every key that is reported as a key is what is called a key set. So each PGP key, it's a combination of keys. And because it's a combination of keys, I have to unpack each key and get all the individual keys that are in each of the main keys. The result is that I had around 9 million keys, and in theory, these keys, because they're using for file encryption, have higher level of scrutiny. And in theory, we shouldn't have any problem with them. So what are the rules? Because we're talking about numbers, the rules are very simple. So every key should be completely unique. Nobody ever should have duplicated key. So if I generate a key today, nobody ever can or should have the same key. And to generate a key, I need 2 numbers. Again, nobody, nothing, ever should use any of my 2 numbers, not even one. If that happens, both keys are broken forever. Nobody can use that number anymore. Now, another requirement, this is mainly for security, is the number should be very big. So if we find anything that is divisible by a small number, the key is implicitly broken because numbers are not very big, so the calculation for the key is wrong. The logic is wrong, so the key is valid. It's not a key that generates error, but is essentially useless. And actually is worse than useless because you don't know it's a bad key, and so you trust the key when in reality you shouldn't. Then there is assumption that the key should have prime numbers. Nobody says that. To developer, it's not a mandatory requirement, so I can put whatever I want. And there are no tests. It's up to the developer to say, I will be very nice and I use only prime numbers. But even if I generate keys with not prime numbers, at the moment, there are no test suite to check this because it's time consuming and it's very resource intensive. And then we shouldn't have anything that uses the number 1. If something uses the number 1, there are big problems. So what happened? If we have any of these conditions that are false, then what we have something that is called a collision. So if 2 keys share a number, or if 1 key has a number that are not prime, what happened? They are insecure. They cannot be used. If they're used, they have to be regenerated. Because if I take this key, I can, because it's numbers, and it's a multiplication of number, I can just divide your key by some numbers to get the original number, and then there is no encryption because by dividing the number, I found your original number. I can regenerate your key very easily. If this happens, the encryption key is useless, and the encrypted data is useless because it's encrypted for the person that is using the key, but anybody that knows that the key is broken, for them, the data is not encrypted at all. They can reverse it whenever they want. So, simple test, downloaded all the key, and check the key by date, creation date. And the result is, out of the 9 million keys, around 900 keys were broken. And this is live data from PGP keys, public. I say creation date because PGP keys are not validated. So anybody can create any kind of key of any kind of format with any kind of data inside it, upload it online, and there will be no check for it. There is no validation. Anybody can create stuff and put it online. So there are keys that are a mix of other keys, that are keys with invalid data, and there are keys with strange data in it. Any key will be accepted in the current PGP ecosystem. The only request is, please follow the format. If you don't follow the format, the key will not be available to other people. So again, anybody that creates a key may have to check for this. First condition, the keys should have only unique numbers, but they don't, because these conditions usually are not tested. So we have a lot of keys with numbers that are shared across keys. A lot of keys have collisions, and this is not only related to broken implementation, but purely by chance, or by system that don't generate enough random data, or not enough random quality data. There are a lot of conditions, but the result is the same. And also the result is the same for keys that are generated by systems that are not checking this, may have problem with numbers. So they're divisible by small number. If this happens, that key is broken, is insecure. Anything signed or encrypted by the key basically is as good as clear text. And key length is not important in this case. If the key is broken, if the mathematical part behind it is not okay, doesn't matter even if you have a 16,000-bit key, because one of the key was 16,000-bit key, it was broken. If the assumption behind it are not okay, encryption is useless, and all the tests and all the assumptions that are not valid anymore. The same logic for the divisors is not rocket science. If I can divide the number by 2, 2 is not very big, so it's not okay. And yes, there are a lot of systems that can be, a lot of numbers that can be divided by 2, by 3, by 5, or by 7. It takes nanoseconds to check it, but it's not implemented by default. So now that we have this idea that maybe there are some stuff that are not really okay, we can scale it to a bigger system. So instead of 10 million keys, we go for 500 million keys. And from that, we remove all the duplicated data, we remove all the stuff that is not okay, then we remain with some valid keys. So at the end, I got around 73 million keys. No idea what is inside. So we are going to repeat the process, repeat the same steps with the same checks. So same questions. RSA key, is the big number unique? So the modulus. Is modulus exponent, so the key, unique? Is the modulus is a product of large big numbers? And is the exponent valid? So first test, combination of keys. Do I have duplicated keys? Yes, a lot. Is it a problem? Not really, because this is considered doable and is not really a violation of any rule. If a company spends a lot of time and money generating keys, they are allowed to take the same key, regenerate the certificate, and so the key is used, but they have a new certificate. So the high percentage of keys is understandable. Also, generation of keys implies that 10 companies can be part of one main company, so they want maybe all to have the same shared key. But each one of them have different certificates with different names, different server name, different system names. But the key is the same for everyone. This is also possible and is allowed. little less common, it's the fact that keys have exactly the same number, so the same modulus. It can happen, same story for the combination of certificates, where you can move the key across systems. If this happens, it means that both keys have been generated with exactly the same number. So if it's not intended, then it means that any keys that use the same combination of number is broken, therefore insecure, therefore anybody can read your data, if they know that there is this problem. Now, how we test for the shared number? Simple. We take the key and we divide each key for any other key. If we are able to find keys that have shared numbers, then it means that any key that has a number is not valid, because you can reverse the process, as we have seen before, and from the public key, you can recreate the private key. So it means there is no encrypted security anymore. Nothing related to security is there anymore. To do this, I tried first in Python. It took me like 3 months to crunch data. It was a little bit too long. So I said, okay, we use something more professional. So I found another project. So it was a very serious and very well done research. They published the code to make the mathematical computation. So I used their code. Code is freely available. When I tested it, it finished in 12 hours. The result is that of all the numbers that I used, around 0.3% had a problem. Now, in percentage seems small, but the result is that more than 200,000 keys were broken. They had shared numbers. So a lot of systems generate keys that are not valid, but they can be used and no alarm will be raised, no error will be shown to anybody. Because to know this, you have to collect all the key and make the comparison between your key and all the other keys. It's very resource intensive. When this happens, you are challenging the assumption of RSA. That is, nothing can be duplicated, ever. The result, scaled to bigger systems. So if you take all the percentage and all the number together, it's that out of the 73 million certificates that I have collected, I got around 800,000, so 758,000 certificates that are not valid. They are used. They are perfectly fine. Nothing will be shown to the user. The lock will be green. The interface will be OK. All the test will pass flying green color. In reality, you have no encryption if anybody knows that your key and your certificate are not unique. Anybody can take it, reverse it, and read your data. And not only read your data, they can impersonate you. So they can sign your mail on your behalf. They can connect to a VPN on your behalf. They can read your encrypted data on your behalf. And nothing will be shown to the user. Now, again, testing for small primes, small numbers, I use primes, and I use the first 10,000 primes. So you can download it. You have it on the internet. They are well known. You just take the numbers and divide every key for these numbers. No software should generate keys without this kind of validation. It takes milliseconds to do this test. But because we don't want to spend the time for this test, we don't want to use these milliseconds, there are a lot of cases with this key that are broken because of these small numbers. And again, a lot of keys are impacted. A lot of numbers are impacted. Now, again, what we have, we shouldn't have anything that uses number 1. So as soon as I get the exponent and I see that something is strange, in this case, exponent equal 1, 28 certificates had this problem. Exponent equal 1, it means that the ciphertext, so what is encrypted, is exactly the same as what is not encrypted. So you use RSA encryption, but there is no encryption. And not only there is no encryption, But the system will say, okay, you have encryption, everything is green, but I didn't encrypt anything because you told me to don't encrypt anything. And not only that, but because the exponent is 1, you can recover the key because all the mathematical part is broken. But it's very fast because you use 1. So some companies have been doing this for years. Some very big software project did this for years. No alarm was raised, nobody was checking. Now there are still 28 certificates there. What it means that you have encryption, but unless you check the encryption, or you check what you see flying through the server, you will never know that there is actually nothing encrypted between the communication endpoint. And this amounts to a very, very small percentage for my data set, but it's also true that my data set is only covering a handful of protocols, only on systems that have been scanned using IPv4 address, only on very small amount of time. So the amount of real certificate in real data can be 100 times what I've seen. So this is just a sample. It's a small sample compared to what you can have in reality, but it's using real numbers. So this is the summary. Numbers seems bad, but in reality, they are definitely much worse. Mainly because my data set seems big, but is very small compared to what people are using. I didn't collect ephemeral keys. I didn't collect temporary keys. I didn't collect application keys. So millions of other sources use it. Like, I didn't collect the files that are signed with the technology of Microsoft for signed file. I didn't collect even Bitcoin keys. Even Bitcoins use this stuff. I didn't collect any of the cryptocurrency. There are millions of other places where you can collect keys. Now, should we panic? No, because this has been already tested. This is already checked. The numbers in percentage are similar. In quantity, it varies over time. But there are very well-done research already available online. They explain all the process, they explain what is available, and they explain some of the issues that they found. Now, taking this idea that we have to check stuff, but we don't really know what to check, and I don't expect anybody to be a cryptographer. I'm not a cryptographer, I'm a network guy, but because I don't trust the technology, I want to check if it really works. So if we exclude the math stuff, what else can be done? What else can be tested? So if we assume that we're dealing with numbers, then can I see the numbers? Can I see these numbers, where they come from? How much number we have? What is the range of numbers? And then what happens if I generate a lot of keys? If we assume that everything is perfect, then if I generate a lot of keys by myself, I shouldn't see any problem. Everything should be unique, everything should be fine. So we start with very little stuff of math. If we have 2 random distribution of numbers, I didn't say prime, I say numbers, we should have at the end something like a triangular distribution. But if we take, for example, very small keys from the collected dataset online, we have sort of, kind of, more or less triangular distribution. But it's not really triangular. So I just give you an idea. It should be what you see in the red line, but the reality is a green part. Now, there is a gap in the center, at the beginning, and then you have 2 different distribution of number, because the dependency and the tendency, they're different. Why is that? Looking into implementation, I saw only the usage of this, so how they implemented it. But if you check for the theory, in theory, this is a mathematical optimization. If you do it, then you are more likely to have good keys. So your crypto is more likely to be good. But what you have, it's a reduction of space of around 12%. So the gap in the beginning, if I reproduce and I create the key by myself with, for example, OpenSSL, but I can do the same with GPG or with SSH, you have this gap. But this does not explain the difference in the shape of the distribution. I'm still working on this stuff. There is no clear definition of what should be good or bad. As far as I know, there are no tests for this, and this is not really been tested extensively. So if anybody has an idea, come to me and we can have a chat. Why is this stuff important? Because if I only focus on this, I don't need any math to check if the system that is producing the keys is good or bad. I take the number, I plot it in a graph. If the number is the beginning or the end, so in the extreme, the system is broken. So in the collected information that I had, 1023 bits modulus, then we have a lot of system, around 7,000 keys, that are compacted, compressed, all at the beginning. That implementation is broken. We don't need anything else. That is not okay. And this is a very good idea if you want to test. You don't need anything, no special things. You just take a number and you see where it falls. The other idea is the key space. So if I have X amount of space for the keys, usually say if you have a 1024-bit key, a 2048-bit keys, then the space for that key is very limited. It's defined and is clearly specified in a lot of documentations. So basically, to have a 2024-bit keys, to have a 1024-bit keys, doesn't matter the size, you stay within a range, predefined range that can be pre-computed, that can be analyzed. So why don't do that? And this is what I tested. So I took 4 systems from oldest to newest, and I let them crunch and generate keys. The result is that in all system, in all situation, with CentOS 7, but I did the same test with other Linux systems, with system up to date, all the patch applied, as system configured with a software random number generator, generating key produces collisions. The machine was working, the system was running, entropy level were okay, but still I had collision. Is it related to the architecture? Maybe. Is it related to the entropy, to the algorithm of the software? Is it the system itself? We don't really know. I'm still testing all the pieces, but seems that it's possible to generate collision by simply generating keys. So the more keys you generate, the more collision you have. The more collision you have, the more keys you can break. Because every time you generate a key, you also generate 2 numbers. And if anybody on the planet ever has the same 2 numbers, I can break their key without them knowing that I have these numbers. It's kind of a rainbow table. It's enormous, but if this happens, then this can be done. So what is happening? In theory, we should have no duplication, no keys divisible by numbers that are small, no key that share numbers, and we don't have anything that has an exponent equal to 1. If that happens, all the assumptions are void, false. Nothing can be used anymore. The same story is, as far as I know, nobody has tested before the long-term collection of keys. So if we have a system that is big enough to collect enough keys over a long period of times, what happens? That by collecting keys, you will immediately be able to know, in the moment the keys are created, if any key is broken. What it means that doesn't matter if you have a self-signed certificate or an extended validation certificate. Doesn't matter if you have an OpenVPN or an encrypted firmware. As soon as you have one key generated, if an entity is able to collect enough keys, they will have enough resources to make a system that says, do you have this key? No. Okay, let's compare this key with everything we have. Maybe it takes a week, maybe it takes a month. And it will have at the end, the answer is, yes, I have it. And if the answer is yes, it's yes forever. So it means that key and all the number related to the key cannot be used anymore by anybody. And any traffic or anything that was encrypted with that key is, at that moment, insecure, invalid. And anybody that uses or touches that key, all the assumptions of cryptography are not valid anymore. So you cannot trust the key, you cannot trust the data signed by the key, written by the key, or even processed by that key. Because somebody somewhere has the private key from the public key. So it means you take the system, and by collecting enough data, you can have the private secret information from the public information. Cryptography is perfectly fine. Mathematics is perfectly fine. The implementation is not okay. By collecting enough data, again, the math part is perfectly fine. There are no problem with that. The implementation is okay because this should be tested during the key generation. It's not tested, therefore we have problems. Same story, it happens if we have temporary keys. The more keys you have, the higher is the probability that there is someone somewhere that has something related to your key. Nobody's collecting, we hope so. Somebody's collecting, we don't know. At the moment, I have not been able to find almost any implementation that makes this kind of test because it's really resource intensive. For me, making this test, it took 2 years to prepare the system, to collect everything, to crunch the data. One run and crunching data is around 6 months. The result is millions of keys that have problems, hundreds of thousands of keys that have considered fine, proper cryptographic key, secure, that in reality, they're not. Problem is, I will not post this stuff because, of course, if anybody has a number, then they can start to attack cryptography everywhere. You cannot give the stuff to entity or companies. Anybody can do it because the information is public. The key is public. Everybody can have it. If you have a system like this, in Europe, you can have problem, legal problem. Another part of the planet, I don't know, but it is very sensitive and very delicate. And if the attacker has enough resources and is willing to spend the time, then it's possible to mount this kind of attack. So if you have any idea or you want to have more information, you have my mail. Get in touch with me because this is an ongoing project, so I'm going to have more tests. And a paper is on the way. As soon as I get the proper confirmation, the proper green light from everybody. It will be taking some time, but yeah, something will arrive. So this is all what I have. Questions? I hope you are not shocked. Yeah? Yeah. So the question is, why they prepend the string? They don't prepend it because when you generate a prime number, it should be random, but we don't want to make it random. So we decided in the beginning that we set the first and second bit to 1 and the last bit to 1. So always, at the end, you have the modulus that start with 1, 0, 0, 1. That is exactly the cut in the graph. That should be a mathematical optimization to make it faster, not more secure, to make it faster. We don't know what is the implication. I have not been able to find anything anywhere that is talking about this. So in theory, from university courses, this is what you should do to make it fast. Apart from that, there is nothing. So we don't know. Yeah, question? Yeah.
Around 2009, Debian opened SSL for federated keys, and the random number they were using wasn't random at all. I wonder are those keys that you're testing still around and in those tests? They will certainly give an applications, as we call it.
Yeah. So the question is, around 2009, Debian had a problem with random number generation, and they were producing keys that have a fixed amount of bits. Therefore, if from the key, if you know the key size, you can generate the key, and you can reverse the key. How this is in my data set or how this is in the information that I have. I excluded that key because that would be too easy. And because there is another assumption on that keys, you're assuming that they're coming from Debian systems. But we have no way of knowing if they're coming from Debian systems. So if you assume that that key has a hash that matches Debian system, you're making an assumption that cannot be verified. So what you can do is checking the numbers without considering even the hash. And this is what I've done. I put aside all the blacklist for Debian keys, and I went to check straight the numbers. Because in that case, you have the real picture. Because unless you know that the keys come from Debian system, you cannot really trust it. Because if you have a duplication of the key, then you have no way of knowing if your hash is related to a Debian key or a real problem. And so I wanted to have a clean slate for that.
I don't understand how you be sure it came from a Debian key.
Because, yeah, because the Debian keys, so the question is, how can you be sure that they are not coming from Debian? Or how can you not sure? Because Debian keys, you can test it against a set of parameters that is specific to the Debian system. If you go outside that parameters, you cannot be sure anymore. Yeah. Question? Yes.
Not to veer into public policy, but if you were a large, well-funded intelligence agency and you found this out maybe 10 years ago, what would you be doing with this knowledge? What would be the risk?
First, I cannot fully answer, but I will try to answer. So, question, if you're a very large entity, we can say entity, and you knew about this 10 years ago, what can you do with this? The answer is whatever you want. Why? Because nobody will be aware of it. There will be no alarm raised by anything. There are no tests. There is no central location. There is nothing to verify that you know this. So you can not even intercept. You can simply say, please, proxy, let me in. You have the key, so you go in. Please, mail system, let me read the email of this guy. Okay, go in, you have the key. I have an encrypted file or encrypted firmware or a file that is being signed, digitally signed. Who cares? You have the key. You remove the digitally signed file that is considered safe. You replace it with malware, and the file is perfectly fine. In reality, it's malware, but nobody will know it. So in reality, it's use your imagination, anything can be done with computer. And the problem is, we have no test at the moment to verify this. There is no condition that can raise this alarm. At least not that I'm aware of. Did I answer your question? Yeah. Yes.
Maybe I missed that part, but how did you determine that two modules share at least one prime? So
Yes.
are you able to determine the prime vectors with much number?
You can.
But this is basically baseline for security apparently, right?
Is that, okay. So question is, if we have a very big number of RSA, how can identify the prime component of big number? Can you do that? The answer is yes, you can. Why? Because it's just a number. If I take the number and I divide the number for all the numbers that I have, if I have two numbers that are sharing a number, I don't have to know anything else. The math will tell me, for example, I multiply 3 and 5 and 3 and 7. If I divide these two numbers, so the multiplication of 3 and 5 and the multiplication of 3 and 7, they will both divide 3 because it's a number that I used. I don't have to know anything else. It's a very big number, but it's the same logic. Very simple, very easy, no magic. But to do that, you have to have the data set. And to have the data set, if you are in Europe, you are in trouble if you make any correlation. If you say, who has a problem? if you say which certificate is a problem, if you say which company is a problem. You cannot say any of that. You say only these numbers have a problem. That's it. That can be done.
What would be your recommendation to avoid this? I mean, the overall number of known problems is not that large that we can equip an increasing number of certificate devices with completely distinct crimes.
So the question is, now that we know this, what can you do about that? Can we use math to compute numbers and find all the numbers? The answer is yes and no. Why? Because first, you are not using random numbers, you're using prime numbers under certain conditions. So it's not an infinite amount of numbers, it's a finite number. The amount of number is finite, it's not infinite. So if you have enough space, you can store all the numbers. Assuming you have not enough space, then again, is the logic correct? We don't know. Are the prime number generator okay? We don't know. Because they've been tested for randomness, they have not been tested for quality. Why? Because you cannot test for quality because you have nothing to compare them. So yes, you can store and produce keys as much as you want, and then over time you will have enough numbers to break millions of keys. You will not be able to quantify how many in reality or how many there remain. But it can be done. But you need a lot of resources and time, regardless of how big the number is. This is purely a resource constraint. Yeah. Yes, question.
I have just a note. We tried generating many keys from the libraries in Branca that are correct. And so we have found no collisions if the random generator was properly. So I think the problem is the generator.
So, yeah. So the comment is, we tried to generate a lot of keys. We generated a lot of keys and we had no collision. So maybe the problem that I found is related to the prime number generator that I have or the system that I have. I perfectly agree. But this test has not been done in a large scale, and we don't know what are the comparisons, because by using general system with general configuration well after they've booted, with the system well up and running, I found them. Is it my system? I use 4 computers, 4 different technologies, different stuff, and still I found them. Maybe it's my computer because I don't have a hardware random generator. Maybe it's my software random generator. I'm still testing that. So no attribution, no pointing what. I'm just saying, by using normal systems, I found this. I repeated the test 3 times, several times over the years, and I still find them in my systems. In other systems that have a hardware random generator, I never seen it. In very good systems that are using FIPS with good amount of entropy, I've never seen it. So maybe there is a balance for this. So, is it okay? Yeah, answer? Yeah? Okay. Okay. So we reached time, so we can continue after that. Yeah.
Thank you, Enrico.
Thank you.